Welcome to this session on escape speed. This is not the speed I see students leaving my room when they have a lesson with me period 4 on Friday. It is actually something scientific. Who'd have thought that? The escape speed is the speed required for a projectile to leave the Earth's gravitational attraction. So that means to get to infinity. Seems quite something, but we can work this out. So let me take you through the steps. So we want to get to infinity. We can work out the potential of the Earth's surface we recognize is minus the gravitational constant multiplied by the mass of the Earth divided by the radius of the Earth. That means that the change in potential to get to infinity is going to be equal to that potential multiplied by the mass of the object we're trying to get rid of. And so mass is m is the mass of the projectile. So if we know the mass of the projectile and we know the mass of planet Earth, we know the radius of planet Earth, it means we can work out the amount of energy which is going to be required to get to infinity, or the change in energy. Now this is kind of useful because this amount of energy is going to be equal to the amount of kinetic energy it first has, okay, because kinetic energy is going to convert to potential energy on this journey. So therefore half mv squared equals g mass of the Earth times the mass of the object divided by the radius of the Earth. We can simplify this and rearrange it to show that means the velocity, the escape velocity, is equal to the square root of 2 times g times the mass of the Earth divided by the radius of the Earth. We can also use the fact that we know that little g is equal to gm mass of the Earth divided by the radius of the Earth squared. So we end up getting a formula which looks a little bit like this. Okay. The velocity of the escape velocity equals the square root of 2 times little g times the radius of the Earth. So now we can work out what the escape velocity is, given some parameters. Let's give a go at this. Here's a problem. Find the velocity of a tennis ball. Must be thrown vertically upward to escape from the Earth. Okay. Well, we recognize the Earth is g is 6.67 times 10 to minus 11. Mass equals 6 times 10 to the 24 kilograms. And the radius is 6.4 times 10 to the 6. So, assuming you came up with a sensible number for the mass of a tennis ball, you should have worked out it needs to be sent up at 11 kilometers per second. Now, this fact works not just on Earth, but works on any planet. So, if I put numbers in, I can find the escape speeds for a number of different planets, moons, and the Sun itself. For the Sun, I'd have to be travelling at 618 kilometers per second. And as you can see there, the mass and the size of these planets has a big factor. Now, how's this also useful? Well, there's things to think about here, and there's implications. Really, complete escape speed from an object is not really possible, because the gravitational field is infinite, so some gravitational force will always be felt no matter how far away you can get. So, that's one point to think about. But this also explains why some planets have atmospheres and others do not, because lighter molecules have higher average speeds and are more likely to reach escape speeds and therefore diminish the atmosphere until there's no more atmosphere left. This also has implications with black holes. How a black hole works is we recognize it's the remains of a collapsed star, collapsing under its own gravitational force. And this gravitational force is so great that it has a very large mass and a very small sphere, which means the escape speed exceeds the speed of light. So therefore radiation cannot escape, and therefore it appears black. Now, there is a critical radius at which the escape speed equals the speed of light, and this is known as the Schwarzschild radius, Rs. And this is the imaginary surface of a sphere, and it's often called the event horizon. Beyond that, there is no escape, even for light. So that is escape velocity. I hope that was useful.